improve. China has several years of industrial media experience, and then before coming to the US, he worked for IBM and EDA companies in Taiwan, developing in-house design from diaphragm flow in micronics and fast spice and mental graphic and synopsis. And during his PhD degree, he worked with the design technology for optimization team in synopsis as a technical intern, and also as an AI resident in X. Google Moonshot factory for 9 months, and his research interests include LM for circuit design, DTC pair funding, reinforcement learning for circuit design, and machine learning for real-time design.
Thank you for the introduction. I just made my bio shorter, sorry. So I'm very delightful to share my work here. So this is a work with the colleagues inside of NVIDIA. So I want to thanks to the production team as well, and also some engineers on this work. And this is my outline. So first of all, I will talk about the motivation and the background, and then introduce the proposed novel transformer model-based clustering method, and demonstrate the experimental results, and finally conclude my work. So first of all, for the motivation part, we all know the standard cell are the building block for the modern design. For example, AND or A flip-flops and adder. And as you can see in the GA100 design inside NVIDIA, there are 1.7 billion standard cells in the design, and which means that standard cell PPA quality is very important and essential to make the block level design better. So as a result, recently, even nowadays, the standard cell library designers still use still trying to struggling to deliver like very high quality and competitive PPA standard cell libraries in a short amount of time. They usually take like months to deliver a high quality cell library. As a result, there are many benefits to do the standard cell layout automations. So first of all, it can improve the productivity and also the performance. And also the most important thing is enable the DTCO design technological optimization to optimize the design library and the design together. But now, as you can see, standard cell layout face a lot of challenges from the technological advances beyond the 5 nanometer. And first of all, because of the limited in-cell routing resource, in the RDS roadmap, actually standard cell ties keep shrinking, so it makes the reliability becomes an important issue. And also, there are a lot of increasing number and complexity of design rules plus the strict patent rules. And finally, it's the scalability. So, as you know, like in the industry, standard cell library, they have like sales more than 100 transistors inside the library. And we found out we need a better and more efficient standard cell layout automation framework for the reliability and scalability and high quality PPA. But the key question is how to achieve this. We found out like high quality device clustering could be one potential solutions for this. For this like high quality device clustering, we need to consider the diffusion break, diffusion sharing, and also internal transistor pin access, and the routing metal DRCs together. So it's not only the NAND, it's logic level. And with this approach, we can reduce the complexity and narrow down the circuit space and assist finding the reliable and optimal cell layouts. So here we propose using the transformer model to generate the high quality clustering results. So now, let me start to introduce our approach. So this is the overview of our proposed methodology. So firstly, we have the SPICE netlist and also some layout specifications, like for example, number of M0 tracks and like M1 gear ratios, and for different settings for the cell architecture. And then you will, this information will fed into the novel transformer model. And here, there are two parts. The first part is the transformer model encoder architecture, and to generate the representative device embeddings. And the second part actually is the personalized PageRank algorithm to consider the netlist logic and the predicted preference vector from the transformer model. And later on, this is cluster results will be fed into the FPCell framework, which developed in DAG and SPD last year. Inside, we have a reliability-driven engine and also genetic algorithm-based router plus reinforcement learning-based DRC fix. And finally, we generate the cell layouts. So here is the transformer model encoder structure. So firstly, if you see the goal of this model is to learn the relationship between device pairs in the layout graph. So firstly, let me define the netlist logic graph and the layout graph first. So for the netlist logic graph, it is from the topologies from the SPICE netlist. And the nodes are the NAS and devices, and pins are represented as the nodes in this graph. And the connection is connection in the SPICE netlist is represented as edges. And there are different type of edges, like pin to NAND and diffusion to get those kind of different connections. But in the layout graph, actually, it's quite different. As you can see, there are PFAB row and MFAB row. And every column is a gate terminal. And if you see, every grid point is kind of connected to the neighbor grid points in the layout graph. And in this architecture, firstly, even the SPICE netlist, and we will extract the netlist logic graph, and then we will fed into the gene network and to generate the graph embeddings, and we treat it as a sequence to input it to the transformer encoder architecture. And here, because the graph there's no like sequential, so we didn't add the positional encoding in this model. And after that, we will generate the representative embedding of each devices. And here we train our model in unsupervised fashion and with the similarity loss. So inside the transformer, actually, what we did is another netlist and layout graph multi-head attention mechanism. So besides the basic self-attention, we add another spatial relation attention bias and also the device placement attention bias to generate a high quality cluster considering the layout effect. For the spatial relation bias, it is shortest path distance between the devices in the netlist logic graph. And for the device placement bias, actually, it is like related to the device layout characteristics, such as the diffusion sharing or whether we can share the vertical gate and or diffusion connection. Then let me introduce the second part. So the second part is the netlist and layout aware personalized PageRank vector clustering. So I know many of you probably are very familiar with the PageRank. It's from the Google, the great invention, one of their great invention. So here, basically is we calculate the personalized PageRank vector of each devices based on the NetList logic graph and the predicted preference vector from the transformer encoder. With this, we can see we can consider the NetList logic and also the layout effect from the prediction predicted from the transformer model as well. And after that, after we have the personalized PageRank vector of each devices, we can start using the DB-scan clustering methodology to cluster, to generate the clusters. And here, this figure is an example of PCA example of the cluster, one of the cluster results of around, I think it's 100 devices latch cells. And here is one of the example we generated, LBS DRC clip layout in the 5nm technology nodes. As you can see, actually, we got the smaller cell width compared to the industrial library, which is pretty impressive because usually in the industrial library, all the cells are like highly optimized by experienced human designer. Now, I will talk about the experimental results. So, firstly, I want to talk about the setup. So, we trained our model using 250 circuits in 5nm library. And we firstly applied this model to a larger and more complex circuits, and also applied to the different technology nodes. So, in the experiment one, we are mainly focused on the 5nm technology node, and we use our approach on the 94 complex cell benchmark, and also the entire cell library, which is around like 1,000 cells. And in the second experiment, actually we apply our model directly to the 3nm technology node without retraining the model. And the third one is the PPA comparison of the 3nm. So for the 5nm technology node, as you can see, in the left side, it is the result of the 94 hard to route cell benchmark. Before DEC 2021 MD-cell, it cannot like finish routing, finish any like LBS and DRC clean cell at all. This is 94 cells. And then after applying some reliability-driven algorithm, we can improve the success rate to 87.2%. And then using the proposed method, we can generate 100% of them. And as you can see, also we got better, more smaller cell width compared to the previous works. And for the performance side, averagely we got 12.7 times speed up on the cells, more than 80 devices. And for the entire cell library, we can generate 100% of the 1,078 cells. They are all DRC LBS clean. For the 3nm node, actually we have different zero architecture. As you can see, we can also generate all of them and also provide pretty good PPA in terms of the cell area. And for the real characterization result between our cell, our generative cell, and also the first version of the custom design cell in the 3nm internally. So we found out the power can improve up to 12% and delay improve up to 8%. And we got some pretty good area benefit as well. So now let me conclude the talk. So firstly, we proposed a novel transformer model-based clustering method to successfully consider the reliability and also self-level PPA together. And it is transferable to different technology nodes, which means it is quite robust to use this model on different technology nodes. Also, it provides some competitive PPA results in our study. some of the future work could be including the PPA-driven standard cell layout automation. So we do see some delay degradation on some sequential cell. So we can, in the future work, I think we can take on this problem to generate like better cell for the sequential cell. And also the cluster constraint debugging and optimization for PPA is the outer loop of this board. So the final one is GTC is next week. So and virtually it is free to register. So if you are very interested in the generative AI or LLM related technology, so please do register the GTC. Okay, thank you.
Any more presentation? Is there any question about this?
Hey Mark, it's very nice work. I would like to check with you, are you only checking the DLC? How about the some kind of logic and reliability to train XLT, all the stuff? How can you make sure the other constraint if you use a smaller cell in area that can meet the requirement?
Yeah, on that part, I think currently our production team didn't consider that part as a very important one, but I think in the future, like for the chiplets or like more like integration, 3D integration, we will add that into the consideration.
And second thing, since you using the like a machine learning master to do that, I would challenge you for conventional the problem that haven't been solved. Actually, we don't have a large cell optimization paper in the EDA industry, which is very important. I will challenge the whole a holistic approach to see, because all the cells need to be about together to make the design work. So that's our boundary constraint need to be co-optimized. So I would suggest you consider that. We can do that.
Oh yeah, okay, sure. Thank you for the suggestion.
Thanks for the presentation. I wasn't sure from the results, did you plug those standard cells into a design and run place around, or this is just the results were based on the individual cell themselves?
So actually, what we did is we did chemical validation, and also for the power and delay. And actually, for the pin access part, we have guaranteed like minimum like 2 pin access points for each external field.
Okay, but you might be able to squeeze down the cell area as much as possible, but that can result in overall larger design because of congestion issues. Even if you have pin access, 2 pin access per 2 access points per pin, it might lead to lower utilization overall of the block.
Yeah.
So, do you do that? Do you have any results that show how it looks like after you plug it in?
Yeah, we don't have that results, but I think this is a very important issue we need to consider. So firstly, here we just to make sure the pin access, like we have like enough pin access point for the external pins, and also we have like a weighted matrix on the metal 2 and metal 1 to let the router not using the metal 2 and metal 1 to relieve the routing congestion in the block level.
Okay, thank you.
I think we have time for one more question. Okay, then thank you again for